This is lecture 16 of condensed matter physics 1, and what I am going to do today is solve 3 or 4 problems based on material covered in lectures 14 and 15. First, I want to devote some time to diamond structure, and what we saw in the previous lecture is that I can think of the diamond structure as 2 FCC lattices shifted with respect to each other by 1 by 4, 1 by 4, 1 by 4. So, this is shifted along this diagonal, body diagonal. So, if I have a point here, the other point is right here at a distance of 1 by 4, 1 by 4 and 1 by 4. Then the nearest neighbors are going to be 1 FCC point here on this face, 1 FCC point here. Then along with these, all these face centered points also, right along the diagonal, there is one point at 1 by 4, 1 by 4, and same thing for the front face. And what we had learnt yesterday, there are 8 atoms per conventional cell. So, the nearest neighbors are 1 by 4, 1 by 4, 1 by 4 vector away from each other, and that you can see easily. All right, all the other distances are larger. So, if you look at a set of nearest neighbors, I am going to have one right here, one is right here, one is below down here, and one is going to be on this surface. So, the way you can look at it is each one of this is that these atoms or nearest neighbors are located as follows. There is one at the center, and then you form these body diagonals, all 4 of them. From here to here also, the other way, and one like this. You start with one atom at a corner, and then you go to the alternate diagonal. So, other one would be right here, third one would be right here, and the fourth one over here. Let us see, this is right opposite this diagonal, so it is not going to be here, it is going to be somewhere else. Let us see, this is going to be, I am going to go to alternate side. So, this is probably going to be here. So, what they form is a tetrahedron, and these are the bonds. Okay, this is precisely what the set of atoms out here gives you. So, the first problem I am going to do is find the angle between bonds of nearest neighbors. And once I have made it for you, it's very easy. I can either look here or look here. So if I take the corner atom to be 0, 0, 0, similarly on this diamond side, I take 0, 0, 0, then the vector from the central atom to the corner atom is going to be, so let's call this vector u, is going to be 0, 0, 0 minus either a quarter or 1/2, it doesn't matter, because normalized vector is going to be the same. So this is actually minus 1, minus 1, minus 1 divided by root 3. I'm dividing by root 3 by to normalize it. Now the next atom here is this one, the big green one that I'm showing on the left of the screen, and that vector is 0, 1/2, 1/2 minus 1/4, 1/4, 1/4, and let you derive it for the other one also. It's the same answer. So this will come out to be minus 1 normalized, minus 1, 1, 1 over root 3. So you can see the magnitudes are the same, and these are the nearest atoms. Now finding angle between these two vectors is quite easy. So I have in this FCC lattice the vectors minus 1, minus 1, minus 1 over root 3, and the other one is minus 1, 1, 1 over root 3. So the angle between them is going to be such that cosine of theta is this u dot v, and that comes out to be 1 minus 1 minus 1 over root 3 times root 3 equals minus 1 over 3. So the angle is going to be cos inverse of 1/3. And these are precisely the angles in a sp3 hybridization in methane and all that. So this is precisely that kind of bonding that takes place between the carbon atoms. Next, I'm going to do is packing fraction in diamond lattice or diamond crystal. So if you recall, yesterday I had done BCC or simple cubic, BCC, and FCC. And the packing fraction kept going up. So for simple cubic it was least, then I had body centered cubic, and then I had FCC. Because the number of atoms kept that the cell had kept going up. At the same time, the distances also increased, but distances did not increase that much, and therefore the packing fraction kept going up. Number of atoms were 1 in simple cubic, 2 in BCC, and 4 in FCC. The diamond lattice, diamond structure, has 8 atoms in it. 8 atoms. So let's see what the packing fraction is. Now, the problem that I just solved, where we calculated the angle between two bonds. So nearest neighbors, are along the diagonal. I mean, there are others also, but I can choose them to be along the diagonal, and the distance is along this 1 4 1 4 1 4. So, if the side of this cube is A, then the nearest neighbor distance is equal to A root 3 divided by 4. And this must be at least (2r), where r is the radius of the atom. That's the best occupation that you can have. So, we have A root 3 by 4 equals 2r. R is the radius of the atom, and therefore, the size of the lattice is 8 r over root 3. So, packing fraction therefore is going to be 8 atoms in the cell. Each one has a volume of 4 pi by 3 r cubed divided by the volume of the cell, which is going to be 8 times 8 times 8 r cubed divided by 3 root 3. And what you get is this 8 cancels, this 4 gives you 2 here, then similarly this 3 cancels, and you get this to be equal to pi root 3 over 16, because this guy cancels 2. That's the packing fraction. So, that's roughly 1.7 times 3.1, 51 over 16. So, that's 3.4%. That's the answer. Next, this problem has to do with identifying Bravais lattice, and this is Ashcroft Mermin, chapter 4, problem 1. I am doing it partly, and the rest of the problem is going to be given as an assignment problem. So, the problem says, in each of the following cases, indicate whether the structure is a Bravais lattice. A, base centered cube, and what is that? That is a simple cube with additional points on the horizontal faces. So, what we are talking about is a cube like this. So, obviously, there are these points at the corners, and additionally there is one point on the top and one at the bottom surface. Let's look at the solution. So, recall what a Bravais lattice is. In a Bravais lattice, each point has the same arrangement and orientation around itself. So, that is the environment remains the same. Now, let us look at this problem that we are talking about. I have this cube, the points here, and additional points at the bottom and the top surface. And what we want to know is, if I stand at this point and move to the other point, move to this point, do I see everything the same? To see that, I have to make it a little bigger. So, let me do that now. So, I have this one cube. Let me make additional cubes in different colors so that we do not get confused. Let us make one in front. And so on. Now, if I look at point A here, this has a point to the north, south, east and west, and additionally there are these points at northeast, northwest, southeast and southwest. Do I see the same thing for these additional points that I have put in? So, if I look at the point out here, which I am going to now encircle in blue in the middle cube, I again see that there is going to be one point on the next face here, one point on the face here, one point on the face here, one point on the face here, and then there are these points on the diagonals. So, in the horizontal plane, it has the same orientation. How about the vertical plane? Now, vertical plane also is the same thing, because all you are doing is you are putting one point below here at the distance a, one point above here at distance a, and then these additional points on the sides. Same thing happens to this. So, no matter whether you are at the conventional corner points or at the points in the middle of the horizontal faces, the orientation of all the points is looking the same, and this implies that it is a Bravais lattice. If it is a Bravais lattice, there is an A here. We should also write a primitive cell for this, and that will be given as an assignment problem. Next, we are looking at side centered cubic. And what that means is that there are additional points to simple cubic on the vertical faces. So, I have this simple cubic cell I have the points at the corners, and additionally I have these points on the side faces, and we want to know whether this is a Bravais lattice or not. Although this arrangement could be repeated throughout, but it may not be a Bravais lattice. Remember, when we considered graphene, there also there was a pattern which was being repeated, but it was not a Bravais lattice. So, if I find the corresponding Bravais lattice, it has to be with the basis if this is not a Bravais lattice. So, let us again look at this with different number of cubes, so that we can see the orientation. Let's make a few more. Let's see. Now, what I have is the points at the corners, and the points here. Points at the corners, and points on the side face. And all these points should have the same orientation and same arrangement. So, let us look at point A here and a point on the side face here, B. If I look at A in the horizontal plane, it has one point here on the side. These are the nearest points, and then it has some points on the diagonals. On the other hand, if I look at point B, in the same horizontal plane, it has these points, they are coming from the faces. Then it has these diagonals, but the orientation is changed. So, the orientation of points between A and B appears to be different. And I am using the word appears to be different because I would like you to check it also whether I am right or not. So, at B you have along the diagonals faces, on A also you have along the diagonals, that looks the same. On B you also have a horizontal diagonal which does not appear to be on the A. So, because on B I have these points on the horizontal diagonals also, which is not the case with A. So, that is why they are looking different, and so I conclude that this is not a Bravais lattice. Although this arrangement will repeat itself and this is a periodic arrangement, it could be a crystal. So, if I want to describe it, I have to find a Bravais lattice and it will be a Bravais lattice with a basis. So, this implies this will have a primitive cell with a basis. Part C is for edge centered and that is additional points on the lines joining the simple cubic points. So, what you have here is this simple cubic lattice, and additionally you also have these points right here. And what we have to check is that about these additional points, whether the orientation is the same or not. I leave that for you. I can give you the answer. It's not a Bravais lattice. I leave that for you to check. All right. Then the next problem is concerned with planes in a crystal, and this is taken from Kittle's book. It says, show that for an orthogonal lattice, and what we mean by orthogonal is that the basis vectors A, B and C, obviously they are not in a plane, they are all perpendicular to each other. So, if I were to write it carefully, A perpendicular to B, B perpendicular to C and A perpendicular to C, they are all perpendicular to each other. So, show that for an orthogonal lattice with lattice constants A, B and C, the perpendicular distance between adjacent HKL planes is d HKL equals h square over a square plus k square over b square plus l square over c square raised to minus a half. So, it is 1 over square root of this. So, let us solve this. Now, I am solving it in a pretty straightforward manner because I have practiced these things quite a lot. So, I would also like you to play around with these figures and practice them a lot. So, best thing is to make a lot of figures in 2D and develop a way of looking at various geometric properties. That will give you some sort of a visualization into this. So, again in this problem also I am going to do the same thing. I am going to take a 2D orthogonal lattice. So, A and B are going to be perpendicular to each other. Let us say the direction in horizontal direction is A and this one is B. These are the basis vectors. Okay, so, let me make A fully, make it more carefully. This is from one lattice point to the other. This is my A vector. And I draw an HKL plane. So, in this case it will be an HK line. Some HK line. Just draw it, maybe 2, 3, 4, 2, something. It will give you an idea as to what these are. Now, next HK line will be the nearest point to this. So, that will be next HK line will be somewhere like this. Next HK line will be the next nearest point. So, that will be here. And so on. What this will teach you is that if you go to the planes next to each other adjacent, the distance between them in the primitive vector direction in the horizontal side. So, if there was a plane here, the next line somewhere would be like this. The horizontal distance, and once you make these, play around with them, you will get that idea, is going to be A over H. And the vertical distance between the nearest plane is going to be B over K. So, you also see how the Miller indices give you this idea about distances and all that. Same thing I can do in 3D. Distances will become A over H, B over K and C over L. So, please do this game, draw it on a sheet of paper and see what happens, right. Then you can do the vectors and all those rather easily. So, once you have understood that, what do we do in 3D? In 3D, what I am given is that I have an orthogonal lattice. That means A, B and C are orthogonal. Let me make A, and I am making them different size A, then I have B, let me make it a little bigger, and C. So, I have vector A, vector B and vector C. And when I look at a plane, this plane is going to cut these in certain ratios. So, this is the plane I am talking about. Let us say this is HKL plane, let me make it neater. This is the HKL plane. This side is A, B and C, and this is going to cut these axes at certain points. Now, recall that HKL means that this is inverse of the distance is cut. So, it is going to be 1 over this is the common. So, H over H K L, K over H K L and L over H K L are going to be the inverse of the distances that have been cut. So, this comes to 1 over K L, 1 over H L and 1 over H K. So, the distances that have been cut are K L along A, H L along B. These are the units. It is an H K along C. Now, these are the units. So, the distances are going to be K L A, H L B and H K C. This is what has been cut. Now, you have these planes. I am going to make another one right here. And what we learned from the two-dimensional case is that these distances are A over H, B over K and C over L. Let me go to the next slide and show it to you. So, I have this orthogonal lattice system. I have cut a plane here. This is my H K L plane, and I can say that this is A K L, this fellow is H L B, and this fellow up here is H K C. So, let me make this vector. Vector here is K L A. The vector here is H L B, and the vector going to the top is H K C. Now, we are ready to solve the problem, because once I know these vectors, I can calculate the perpendicular to this plane. Right. So, to calculate the perpendicular, what I will do is I will take one of the vectors. Let me show it by a thick line. I will take this vector here, and I will take the other vector here and take its cross product. That cross product will give me the perpendicular to this plane. So, let us call these, let me call this u, let me call this v. U vector is equal to H K C in the z direction, let me call that the z direction, minus K L A in the x direction. And so, I am taking this to be x, taking this to be y, taking this to be z. I need to do that so that taking cross product becomes easy. V is equal to H L B in the y direction minus K L A in the x direction. I am now ready to find the normal to the plane, and the normal to the plane and vector is going to be u cross v. I will not worry about the sign right now, because that does not really matter. So, the first one is h square K L B C z cross y, that is x with a minus sign. Z cross x gives me y, so that will be minus h k square L A C y, and x cross y gives me z. So that's minus h k l square a b z. That's the normal vector. So the normal to the plane is, I can take out h k l minus h k l. I am left with h b c x plus k a c y plus l a b z. Normalize it. The unit vector perpendicular to the plane is, I can ignore HKL. So, H B C x plus K A C y plus L A B z divided by square root of h square b square c square plus k square a square c square plus L square a square b square. That is the normal to the plane. Once I know that, projection of any vector connecting the two planes along this normal would be the distance. So, the distance between the planes will be projection of a vector connecting the two planes on n. So, let us do that now. I have this orthogonal system x, y, z. I have this HKL plane here, and the next plane is right next to it. And what we had seen in 2 dimensions, that the distance along the x is going to be a over h, distance along y is going to be b over k, and distance along z is going to be c over l. And I need to take the projection of any of these vectors along that normal, and that normal n is equal to BC H along the x direction plus AC K along the y direction plus ABL along the z direction divided by square root of B square C square H square plus A square C square K square plus A square B square L square. And I will take the projection of, let us say, x, y, or any vector. Let me take the vector in the x direction, a over h, x dotted with n is equal to d h k l. So, d h k l is equal to a b c divided by square root of b square c square h square plus a square c square k square plus a square b square L square, and this is equal to 1 over square root of h square over a square plus k square over b square plus L square over c square, as we saw earlier. Now, one more point I want to make here is that if the lattice is cubic, and which means A equals B equals C, then the normal vector is going to be equal to hx plus ky plus Lz times the normalization factor. There is some normalization factor times the constant. So, in a cubic lattice, the normal to plane HKL is Hx plus Ky plus Lz. So, this is normal to plane HKL. Another significance you see of the Miller indices, that in a cubic lattice, which is obviously orthogonal lattice, it automatically gives you what the normal to the plane is. So, that is an additional point here. So, with this, let me conclude today's lecture. Problems based on Bravais lattice, diamond structure, packing fraction, and planes in a crystal have been solved. Thank you.